Today, we're tackling one of the most, well, ambitious and frankly mind-bending ideas in modern physics. String theory.
It really is.
Imagine trying to find a single, elegant framework that explains everything, everything, from the tiniest particles to the vastness of the cosmos. That's our mission today, to unpack the big ideas, the surprising twists, and yeah, the ongoing challenges of this quest for a theory of everything.
It's quite a journey. We're going from the infinitely small to the unimaginably large. It touches on quantum mechanics, gravity, even the very nature of space and time itself.
And how scientists are using it.
Well, we'll explore how scientists are using this theoretical framework to, really push the boundaries of what we understand about our universe.
Okay, let's unpack this. For decades, we've thought of fundamental particles as tiny, indivisible points, like the ultimate building blocks. But what if that picture? What if it's just incomplete?
That's precisely where string theory kicks off. It proposes something revolutionary. Instead of point-like particles, the universe's most fundamental objects are not points at all.
Okay.
They're one-dimensional strings. Think of them not as static dots, but as incredibly tiny, vibrating strands of energy.
Vibrating strands.
Yeah.
Okay, so these strings move through space, they interact. How do the vibrations relate to, well, everything we actually see? The particles, the forces.
Well, the beauty of it is that the way a string vibrates determines its properties.
How so?
Its mass, its charge, even what kind of particle it is. It's really like a single guitar string. It can produce a whole range of different notes depending on how you pluck it, how it vibrates.
The cosmic guitar string?
Kind of. And here's where it gets really interesting. One specific way a string can vibrate, one specific note, corresponds exactly to the graviton.
The graviton. The hypothetical particle for gravity.
That's the one. The particle that theoretically carries the gravitational force.
Wow. Okay, so if it includes the graviton right there at its basic structure, what does that mean? Does that automatically make it a theory of quantum gravity?
Absolutely. That's the crux of it. Including the graviton makes string theory a very powerful candidate for unifying Einstein's general relativity.
Which describes gravity, the big stuff.
Right. Gravity and space-time on the macro level with quantum mechanics.
The physics of the very small.
Exactly. It's attempting to solve one of the deepest problems in physics. How do you get these two fundamental theories to talk to each other? How do you reconcile them?
And it's funny how these things start. Tell us about its origins. It wasn't aiming for gravity at first, was it?
No, not at all. It's quite a surprising backstory. String theory first popped up in the late 1960s, early 70s. And it was actually developed as a theory for the strong nuclear force, the force that holds protons and neutrons together in the nucleus.
Right. Hadrons.
Exactly. But it had some issues, and it was eventually sort of pushed aside in favor of quantum chromodynamics, which worked better for the strong force.
So how did it make the jump to gravity?
Well, ironically, the very things that made it not work for the strong force.
Like what?
Like predicting a massless particle with spin 2, which is exactly what the graviton should be. Those problems turned out to be its greatest strength when people started thinking about quantum gravity.
So it found its true calling, so to speak, and it evolved from these initial bosonic strings.
Yes. The earliest version, bosonic string theory, was simpler but incomplete. It only described bosons, the force-carrying particles.
Okay.
The next big step was developing superstring theory. This brought in something called supersymmetry.
Ah, CZY. Heard of it.
Right. Supersymmetry is this theoretical idea that connects bosons and fermions. Fermions are the matter particles, like electrons and quarks.
So every particle has a partner?
Theoretically, yes. Every boson has a fermion superpartner and vice versa. Adding supersymmetry made the theory more mathematically consistent, more robust, and it led to, initially, 5 distinct but consistent versions of superstring theory. Type I, type IIA, IIB, and 2 flavors of heterotic strings.
5 versions. We'll come back to that. But first, okay, strings vibrate. That gives us particles. What about the space they vibrate in? Our universe feels pretty 3D, plus time. 4 dimensions. Where do strings live?
Yes. Here's another, properly mind-bending aspect. For the math to work, for string theories to be consistent, they require extra dimensions.
Require them, not just allow them.
Require them. The early bosonic string theory needed space-time to be 26-dimensional.
26.
Yep. Superstring theory calmed down a bit, but still needs 10 dimensions. 6 extra spatial dimensions, plus our familiar 3 space and 1 time.
10 dimensions. Okay. How on earth do we explain why we don't, bump into these extra dimensions when we walk down the street?
Right. Fair question. There are two main ideas floating around. One is compactification.
Compactification. Sounds like making something smaller.
Pretty much. Imagine looking at a garden hose from really far away. It just looks like a line, right? One dimension.
Yeah.
But get up close, and you see it has a circumference. There's a second dimension there, but it's curled up. It's compact. So the idea is maybe these extra 6 dimensions are curled up incredibly tightly, so small we just can't perceive them in our everyday experience.
How small are we talking?
Unimaginably small. Planck length small, maybe. And for our universe to look the way it does, with the particles and forces we observe, these extra dimensions would need to be curled up in very specific, complex shapes, things called Calabi-Yau manifolds.
Calabi-Yau manifolds. Got it. So intricate shapes, curled up super tiny. That's one idea. What's the other?
The other main idea is the brane world scenario. Brane is short for membrane.
Like a membrane?
Sort of. In this picture, our entire observable universe, all of space and time as we know it, is a 4-dimensional subspace, kind of surface or brane. And this brane is embedded within a larger, higher dimensional space, sometimes called the bulk.
So we're stuck on a slice, basically.
In a way, yes. The idea is that most particles and forces, like photons for light, come from open strings whose endpoints are literally stuck, anchored to our brain. They can't leave.
But not everything is stuck.
Gravity is different. Gravity is thought to come from closed strings, little loops, and these closed loops aren't necessarily stuck. They could travel off the brain into the higher dimensional bulk.
Ah. And could that explain why gravity seems so much weaker than the other forces, like electromagnetism?
Exactly. It offers a really natural explanation for that puzzle. If gravity can sort of leak away into these extra dimensions, it would appear weaker to us, confined here on our brain.
That is quite a concept. Okay, hidden dimensions, brains. You also mentioned dualities earlier, these connections between different string theories.
Yes, dualities. These are really profound mathematical transformations. They show that theories which look completely different on the surface are actually physically equivalent. They describe the exact same physics, just in a different mathematical language.
So 2 different instruction manuals for the same machine.
That's a good way to put it. It means one theory can be transformed mathematically to look just like another one, and they'll make the same predictions for anything you could measure.
That must have been a huge aha moment for theorists.
Oh, absolutely. It was revolutionary. For example, there's something called S-duality. It can relate a theory where particles interact very strongly.
Which is usually really hard to calculate.
Exactly, really hard. S-duality can relate that to a different theory, where the particles interact weakly, which is much easier to handle. Suddenly, difficult problems become solvable.
Clever. Any other examples?
There's also T-duality. This one relates string theory on a space where one dimension is curled up into a circle of radius r to a different string theory on a space where that circle has a radius of 1r. So a universe with a large extra dimension can be physically identical to one with a tiny extra dimension.
Large is the same as small. That's weird.
It is weird,
Yeah.
but mathematically consistent. And these dualities started revealing these deep, deep connections between those 5 different superstring theories we mentioned. It suggested they weren't really separate theories after all.
Okay, so we had these 5 seemingly distinct superstring theories, but dualities were showing they were connected. Was that the end of the story, or did things get even bigger?
Oh, they got much bigger. This is where the story takes another major turn. In 1995, Edward Witten, who's a towering figure in theoretical physics,
Right.
he gave a landmark talk. And he proposed something truly groundbreaking. That all 5 of those consistent superstring theories weren't fundamental. They were actually just different limiting cases, different perspectives on a single, more fundamental theory.
A single theory underlying all 5.
Yes. A theory existing in 11 dimensions. He called it M theory.
M theory. Does the M stand for anything specific? Membrane? Magic?
Well, Witten himself playfully suggested it could stand for magic, mystery, or membrane, partly because even today we don't fully know its complete structure or fundamental principles.
But it's a huge deal.
Absolutely massive. His announcement basically kicked off what's known as the second superstring revolution. It led to this incredible surge in research and understanding, tying together all these loose threads.
What were the key insights that allowed for this unification? What pointed towards M theory?
It was really a convergence of ideas.
Yeah.
The dualities we just talked about were absolutely crucial. They showed these hidden equivalences. Another huge piece was realizing the importance of these higher dimensional objects, the brains. Not just strings, but 2 brains, 3 brains, and so on.
Right, the membranes.
Exactly. Physicists had known about something called 11-dimensional supergravity for a while. It's a theory that combines gravity with supersymmetry, and it kind of sets a limit. You can't really have consistent supersymmetry in more than 11 dimensions.
Okay.
And this 11-dimensional theory naturally included two-dimensional branes, or membranes. The key insight Witten and others put together was, what happens if you take this 11-dimensional theory and curl up one of its dimensions into a tiny circle?
Like the compactification idea.
Precisely. If you do that, a two-brane wrapped around that tiny circle looks, from the remaining 10 dimensions, exactly like a one-dimensional string.
Ah. So the strings of the 10-dimensional theories could actually be membranes from an 11-dimensional theory.
That was the idea. M-theory provided this overarching framework. It suggested that the 5-string theories and 11-dimensional supergravity were all just different corners, different approximations of this single, mysterious M-theory.
Did they develop any concrete ways to actually calculate things in M-theory? It sounds very abstract.
Well, defining M-theory completely is still an open problem, but there was another key development around 1997, the BFSS matrix model.
BFSS.
Named after Banks, Fischler, Schenker, and Susskind. It's a model involving basically the quantum mechanics of 9 large matrices. It sounds abstract, I know.
A little, yeah.
But the amazing thing is, in a certain limit, when you look at its low-energy behavior, it exactly reproduces 11-dimensional supergravity. So this matrix model was conjectured to be, in some sense, equivalent to M-theory, at least in a particular setup. It provided a non-perturbative definition meaning, not just an approximation of M-theory in a specific context. A huge step forward.
Okay, so M-theory unites the strings. But string theory isn't just about unifying fundamental forces, is it? It's had a big impact on understanding black holes, too.
The massive impact, yes. Black holes are these incredible natural laboratories for quantum gravity. They pose deep, deep puzzles.
Like their entropy.
Exactly. One of the biggest puzzles was the Bekenstein-Hawking formula. It says a black hole has entropy a measure of its hidden information or microstates, and that entropy is proportional to the area of its event horizon.
Right, area, not volume.
Right.
Which is weird.
Very weird. It implies the information is somehow stored on the surface. But the problem was, general relativity and standard quantum field theory couldn't explain why. They couldn't account for these microstates. You couldn't sort of count them to derive the formula.
So what did string theory bring to the table? How did strings help count black hole states?
This was a landmark achievement. In 1996, Andrew Strominger and Qumran Vafa figured it out for certain specific types of black holes, supersymmetric ones.
Okay.
They used objects in string theory called D-branes. These are like higher dimensional surfaces where open strings can end. They showed that you could construct a system of D-branes that, when interacting strongly, behaved exactly like one of these specific black holes.
So they built a black hole out of D-branes.
Mathematically speaking, yes. And the crucial part was they could count the quantum states of this D-brane system using well-understood methods. And when they did the counting...
Did it match?
It matched perfectly. They derived the Bekenstein-Hawking formula, including the exact numerical factor of 1/4, right out of string theory.
That's incredible. That must have given the theory a huge boost.
Oh, it was monumental.
Yeah.
It showed string theory wasn't just abstract mathematics. It could provide concrete, quantitative answers to deep problems in quantum gravity that nothing else could touch. It made it feel much more real.
And that success paved the way for something else huge, right? The ADA-CFT correspondence.
Yes, absolutely. Building on insights from D-branes and black holes, Juan Maldacena in late 1997 proposed something truly radical. The anti-de Sitter conformal field theory correspondence, or AD-SCFT.
Okay, break that down for us. ADA-CFT.
Okay. Anti-de Sitter space, ADS, is a specific type of curved space-time geometry. It has some weird properties, like a boundary that's infinitely far away but reachable in finite time.
Right.
A conformal field theory, CFT, is a particular type of quantum field theory, one without gravity, that has special symmetry properties. It describes systems at critical points like phase transitions.
And the correspondence.
Maldacena proposed a duality, a mathematical equivalence, between string theory, specifically type IIB superstring theory, happening inside a 5-dimensional anti-de Sitter space, times a 5-dimensional sphere, actually.
Yeah, a 10B spacetime.
And a specific 4-dimensional conformal field theory, a souped-up version of the theory describing the strong force called Na4 super Yang-Mills theory, living on the boundary of that ADS space.
Wait. So a theory with gravity, string theory, inside the space, is equivalent to a theory without gravity, the CFT, living on its boundary.
Exactly. It's like a hologram. All the information about the higher dimensional space with gravity is somehow encoded in a lower dimensional theory without gravity on its surface.
A holographic principle for reality. That's
I,
huge.
it is. It suggests gravity might be emergent, not fundamental in the way we thought. There's like a dictionary to translate questions asked in the gravity theory, the bulk, into questions in the field theory, the boundary, and vice versa.
What has this add-SCFT correspondence been useful for?
So many things. For one, it provided powerful evidence against Stephen Hawking's earlier idea that black holes destroy information.
The information paradox.
Right. The boundary CFT is a standard quantum theory where information is definitely conserved. If it's truly equivalent to the gravity theory with the black hole, then information must be conserved there too. It doesn't tell us how it gets out, but suggests it must.
So it resolved a major paradox, conceptually at least.
Right.
Any more concrete applications?
Absolutely. It's become a surprising tool in other areas of physics. Take nuclear physics.
Nuclear physics. How?
Well, physicists study something called the quark-gluon plasma. It's this incredibly hot, dense state of matter, like a soup of quarks and gluons that existed just after the Big Bang.
And they recreate it in particle colliders, right?
They do, like at RHIC and the LHC. But it's a strongly interacting system, very hard to calculate things about it directly using standard methods.
So add-SCFT helps.
Amazingly, yes. Using the add-SCFT dictionary, physicists could model the quark-gluon plasma using a black hole in a 5-dimensional ADI-S space.
A black hole model for plasma.
Sounds crazy, but it worked. This holographic model allowed them to calculate properties like its viscosity, how easily it flows. They predicted a specific, very low ratio of shear viscosity to entropy density. And the experiments at RHIC measured it around 2008 and found a value very close to the prediction from the string theory calculation.
That's astounding, using black holes in extra dimensions to predict results in a particle collider.
It really is. It shows the power of these unexpected connections.
And you mentioned condensed matter physics, too. That seems even further afield.
It does, but the connection is there. Condensed matter physicists study materials and their collective quantum behavior, things like superconductors or superfluids.
Okay.
Some of these systems are also strongly interacting and hard to understand. So again, people are using the add-SCFT dictionary. They translate the condensed matter problem into a gravitational problem, often involving a black hole in ADI-S space, solve it there, and then translate the answer back.
Give you an example.
Yeah, for instance, it's been used to study quantum phase transitions, like when a material suddenly changes from being a superfluid, flowing with zero viscosity, to an insulator. The holographic approach helped model the dynamics of atoms during this transition in a way that matched experiments surprisingly well.
So string theory, through add-SCFT, is acting like a bridge between gravity, particle physics, nuclear physics, and condensed matter.
Exactly. It's providing this common mathematical language and set of tools to tackle problems in vastly different areas. It's quite remarkable.
Okay, this is all very impressive theoretically, and with these applications.
Yeah.
But is string theory actually trying to describe our specific universe? With the particles we know, the forces we measure?
That is definitely the goal for a branch of the field called string phenomenology.
Phenomenology, trying to connect theory to observable phenomena.
Precisely. The idea is to take the general framework, say, M theory, or one of the superstring theories, and try to make it specific to our world. This usually involves choosing how those extra dimensions are compactified.
Choosing the shape of the Calabi-Yau manifold, for instance.
Exactly. The specific shape of those curled-up dimensions determines the types of vibrations the strings can have, which in turn determines the spectrum of particles and forces we'd see in our familiar 4 dimensions.
So they're trying to find a shape that gives us the standard model of particle physics, or something close to it.
That's the hope. To reproduce the known particles, quarks, leptons, gauge bosons, and their masses and interactions. Maybe even predict new particles or forces beyond the standard model that we could look for experimentally. It's incredibly challenging work, though.
I can imagine. And what about the very beginning? The Big Bang. Can string theory say anything about cosmology? Maybe about inflation?
Yes, that's another active area applying string theory to cosmology. The theory of cosmic inflation, which proposes this period of incredibly rapid expansion in the very early universe.
Explains why the universe is so big, flat, and uniform.
Right. Inflation requires some kind of field, a hypothetical particle called the inflaton, to drive the expansion. String theorists are trying to see if any of the fields naturally present in string theory could play the role of the inflaton.
So, finding an inflaton candidate within the string framework,
Exactly. They look for fields that arise from, say, the shape or size of the extra dimensions or from brains moving around. It's still early days, but the hope is that these models might make specific predictions, maybe tiny signatures in the cosmic microwave background radiation, that could one day be tested.
Fascinating. Now, beyond physics, I've heard, and this always amazes me, that string theory has had a significant impact on pure mathematics. How does that work? A physics theory influencing math.
It's one of the most striking and perhaps unexpected consequences of string theory research. It happens because physicists, exploring the structure of the theory, often stumble upon deep mathematical relationships or patterns that mathematicians hadn't seen before.
So the physicists make conjectures based on their physical intuition.
Pretty much. They might find two seemingly different calculations give the same answer, suggesting an underlying mathematical identity. They propose this identity, and then mathematicians, intrigued, step in to try and prove it rigorously. String theory acts as this incredible engine for generating new mathematical ideas.
Can you give us a concrete example?
The classic example is mirror symmetry. This came out of studying those Calabi-Yau manifolds used for compactification.
The shapes for the extra dimension.
Right. Physicists discovered that you could have two topologically different Calabi-Yau manifolds, really distinct shapes, but when you use them to compactify string theory,
Yeah.
they lead to the exact same physical theory in 4 dimensions. They're physically equivalent, even though the geometries are different.
Whoa. How is that useful for math?
Well, it turns out that a calculation which is incredibly difficult to do on one Calabi-Yau manifold might be straightforward on its mirror partner. This duality allows mathematicians to solve problems in a field called enumerative geometry, basically, counting geometric objects.
Counting things like.
Counting curves of a certain type on these complex manifolds. In 1991, physicists Candelas, De La Osa, Green, and Parkes used mirror symmetry to predict the number of rational curves of various degrees on a specific Calabi-Yau manifold called the quintic threefold.
And what did they find?
They generated a whole list of numbers. For degree 3 curves, for instance, they predicted there were exactly, 317,206,375 of them.
That specific.
Exactly that specific. And these numbers were far beyond anything mathematicians could calculate at the time using traditional methods.
And were the physicists right?
They were. It took mathematicians quite a while to develop the techniques to rigorously prove these results, but the physicists' predictions, derived using mirror symmetry inspired by string theory, turned out to be absolutely correct. It revolutionized parts of algebraic geometry.
Oh, wow. Physics predicting pure math results. That's wild. Is there another example, maybe even stranger?
Oh, absolutely. There's the wonderfully named monstrous moonshine.
Monstrous moonshine. Sounds like something out of fantasy.
It almost is. It refers to a completely unexpected and deep connection between two very different areas of mathematics.
Which are?
On one hand, you have the monster group. This is the largest of the so-called sporadic, finite, simple groups. Think of simple groups as the fundamental building blocks of symmetry. The monster is, well, monstrously large. It has over 8 times 10 to the power of 53 elements.
That's more atoms than in the Earth.
Way more. It's an incredibly complex structure. On the other hand, you have something from number theory called the modular J function. It's a function that encodes deep properties of numbers related to things like elliptic curves and modular forms.
Okay, a giant group and a number theory function. Where's the connection?
The moonshine part was the discovery, back in the 70s, that the coefficients in the series expansion of the J function seemed to be related in a simple way to the dimensions of how the monster group can be represented mathematically. It seemed utterly coincidental, hence moonshine.
So how did string theory get involved in this purely mathematical mystery?
It was Richard Borcherds in the early 90s, building on ideas from physicists like Frenkel, Lepowsky, and Merman, who had constructed a mathematical space related to the monster group. Borcherds used techniques and concepts originating from, guess what? Bosonic string theory compactified on a particular 24-dimensional torus.
String theory again.
Yes. He used vertex operator algebras, which are central tools in string theory, to essentially build a bridge and explain the monstrous moonshine connection. He proved the conjectures.
And he won the Fields Medal for that, didn't he?
He did in 1998, partly for that work. It's just another stunning example of how exploring the structure of string theory, even its less realistic versions like bosonic string theory, can lead to profound insights in completely unexpected areas, even pure mathematics.
Okay, this is all incredibly impressive. String theory seems to unify physics ideas, explain black holes, connect to experiments, even drive mathematics. But It's not universally accepted, right? It faces some pretty significant challenges and criticisms.
That's absolutely true. Despite its successes and elegance, string theory is definitely not without its problems and critics.
What's one of the biggest criticisms I've heard about the landscape?
Yes, the string theory landscape. This is probably the most debated issue. As we understand it now, string theory doesn't seem to predict a single, unique universe.
No.
No. Remember those Calabi-Yau manifolds for compactification? There are vastly many possibilities for those shapes, and potentially other choices you can make, like where branes are located, what fluxes are turned on. The result is that string theory seems to allow for an enormous number of possible vacuum states.
Vacuum states meaning possible universes.
Essentially, yes. Each vacuum state would correspond to a universe with potentially different fundamental constants, different particles, different forces.
How many possibilities are we talking about?
The estimates are frankly astronomical. A commonly cited number, though very rough, is something like 10 to the power of 500.
10. Followed by 500 zeros. That's a lot.
It's an understatement.
So what's the problem with having so many options?
Well, critics, like physicist Peter Voigt, argue that if your theory allows for 500 different outcomes, how can it possibly make any concrete, falsifiable prediction about our specific universe? If you can get almost any result you want just by picking the right vacuum state from this vast landscape, does the theory really have any predictive power left? It risks becoming non-falsifiable.
But isn't there a counter-argument? Some physicists see this landscape as a feature, not a bug, especially regarding the cosmological constant.
Yes, that's the other side of the coin. Physicists like Leonard Susskind champion this view. They argue the landscape provides a natural framework for the anthropic principle.
The idea that the universe must be compatible with us being here to observe it.
Exactly. The cosmological constant, which drives the accelerated expansion of the universe, is observed to be incredibly mysteriously small, much smaller than naive theoretical estimates. The anthropic argument within the landscape says, well, maybe the cosmological constant can take on many different values across these 100 and 500 possible universes, but we, as observers, could only evolve in a universe where it's small enough to allow galaxies and stars to form. In most other universes, it would be too large, blowing everything apart too quickly.
So we find ourselves in a rare, life-friendly universe simply because we couldn't exist anywhere else.
That's the idea. So the landscape, combined with anthropic reasoning, explains the small cosmological constant. But critics argue this isn't a real prediction. It's more like giving up on finding a fundamental reason and resorting to a selection effect. Voigt has called it an excuse for failure.
It's a deeply philosophical debate as much as a physical one. Are there other fundamental issues? What about dark energy compatibility?
That's another area of active research and debate. While the landscape potentially allows for a small positive cosmological constant like we observe, constructing fully stable, realistic models within string theory that incorporate it has proven difficult. There was even a controversial conjecture put forward in 2018, part of the Swampland program, suggesting that maybe stable de Sitter vacuum universes with a positive cosmological constant like ours seems to have might be fundamentally incompatible with a consistent quantum theory of gravity like string theory.
So string theory might prefer universes that eventually collapse or are empty.
Or perhaps universes where dark energy isn't a constant but something dynamic, like quintessence. This is still very much debated, with people constructing potential counterexamples. But it highlights the ongoing challenge of matching string theory precisely to our observed cosmology.
Okay, another big conceptual criticism I hear is about background independence. What's that about?
Right. This is a really important point, especially when comparing string theory to other approaches to quantum gravity, like loop quantum gravity.
Awesome.
Einstein's general relativity is fundamentally background independent. What that means is the theory doesn't start by assuming a fixed spacetime geometry, like flat Minkowski space. The geometry of spacetime is dynamic. It emerges from the equations themselves, determined by the distribution of matter and energy. Spacetime tells matter how to move, and matter tells spacetime how to curve.
Okay, that's general relativity. How does string theory compare?
Traditionally, the way string theory is formulated is background dependent. You typically start by defining strings moving and interacting on a pre-existing background spacetime. Maybe flat space, maybe an ADS space, maybe a Calabi-Yau manifold. You calculate perturbations, quantum fluctuations around that fixed background.
So you have to put the stage in by hand before the actors can perform.
That's the criticism, yes.
Hmm.
Critics like Lee Smolin argue this is a major conceptual weakness. They say string theory fails to incorporate one of the deepest lessons from general relativity, that space-time geometry shouldn't be fixed, it should be part of the solution.
But string theorists have responses to that, don't they?
They do. People like Joseph Polchinski have argued that while the standard mathematical formulation, perturbative string theory, looks background-dependent, the underlying physics might not be.
How could that be?
They argue that the sum over all possible backgrounds might be implicitly included, or that different backgrounds are connected by dualities, suggesting they aren't truly fundamental, and they point to things like ADA-CFT.
The holographic duality.
Right. In ADA-CFT, the gravitational theory in the bulk emerges dynamically from the non-gravitational CFT on the boundary. The CFT itself doesn't live on a dynamic spacetime. The dynamic spacetime of the bulk is a result, not an input. So they see ADA-CFT as a concrete realization of background independence in a holographic sense. The debate really hinges on what one considers a truly background-independent formulation.
So another deep, ongoing debate. And lastly, some criticisms aren't just about the theory itself, but about its role in the scientific community, the sociology of it.
Yes, that's also part of the discussion. Some prominent physicists, like Nobel laureate David Gross, who himself worked on string theory, have argued that its continued popularity, despite the lack of direct experimental proof, might simply be because there haven't been compelling, equally developed alternatives for tackling quantum gravity and unification. The only game in town argument. But critics like Peter Woit and Roger Penrose raise concerns about potential bandwagon effects. They worry that the dominance of string theory might stifle research into alternative approaches.
How so?
Well, if most senior researchers, funding agencies, and top journals are focused on string theory, it can be very difficult for young scientists to pursue different ideas, even promising ones, because they might struggle to get funding, find jobs, or get published. It could lead to a kind of monoculture in theoretical physics.
Lee Smolin also contrasted the styles of research, didn't he?
Yes, Smolin argued that string theory grew out of the particle physics tradition, which he characterized as sometimes discouraging foundational speculation, focusing more on calculations within an established framework. He contrasted this with approaches like loop quantum gravity, which, in his view, emerged more from the general relativity community, perhaps more comfortable with radical rethinking of space and time. Of course, these are broad generalizations, but they point to real sociological factors and how science progresses.
Wow. What a journey we've taken. Through vibrating strings, extra dimensions, brains, black holes, dualities, M theory, the landscape. It's really something.
It absolutely is.
We've seen how string theory, for all its abstraction, has genuinely offered profound insights into black hole quantum mechanics, the very early universe, connections between different forces, and even, remarkably, into pure mathematics. It's a testament to that human drive to find a single, unified picture of reality.
It definitely pushes the boundaries of our imagination, doesn't it? It provides this incredible theoretical framework that tries to link the tiniest possible scales, these vibrating strings, to the largest structures in the cosmos. But as we've discussed, it also confronts these really deep conceptual and crucially experimental challenges. Keeps physicists busy, that's for sure.
So what does this all mean for you, listening in? Well, it means the quest for the ultimate laws of nature is very much alive and kicking. String theory is a major player, maybe the major player in many areas, but the story is far from over.
Yeah.
It also sparks these vital conversations, not just about physics, but about how science itself works. What makes a theory scientific? How important is testability right now versus mathematical consistency or explanatory power?
And maybe consider this final thought. If string theory is right about the landscape, if our universe, with its specific laws and properties, is just one outcome among maybe 10 to the 500 possibilities, what does that really imply?
Yeah, what does that mean for how special our existence is? Or for what we can fundamentally predict about the cosmos?
Does it make our universe less significant or more remarkable that we landed in one that allows life? It's a question that pushes right up against philosophy.
A mind-bending thought to end on.